did on the previous lesson, after finding factors, how they compare the factors and the zeros and how we can actually use that with the fundamental theorem of algebra. We learned in the last lesson that if we were to substitute a value into our function and obtain 0, that x minus that value is a factor of the polynomial. The fundamental theorem of algebra tells us that every single polynomial that has a degree of n, that exponent or that degree which is greater than or equal to 1 should have at least one 0 in the set of a complex number. We also know that based on the exponent that we have, that should tell us how many zeros we'll have. And that will also tell us how many factors it has as well. So let's find a polynomial function of degree 3, having the zeros of 1, 3i, and negative 3i. This tells me then that our x values will cross at 1, they will cross at 3i, and negative 3i. Keep in mind the complex numbers, we can't actually see them, so if we were to graph this polynomial, we would only have one real 0 in the form of 1, and 3i and negative 3i would be invisible to us. They're in the complex plane. Then to set each one of these equal to 0, I will have the factors x minus 1, x minus 3i, and adding 3i, and x plus 3i. This is my function that we have to find the third degree, so we're going to need to distribute. I'm first going to use and distribute these. We see that they're conjugates of one another, and we're going to talk about conjugates here in a little bit. But since they're conjugates of one another, we know that some principles will apply because some things will end up canceling themselves out. Gives us x squared plus 3xi minus 3xi minus 9i squared. I know this I squared value will give us a negative 1. Combining like terms, I'll still have x minus 1 out front, but then I'll have x squared, or 3xi minus 3xi, create a 0 pair, plus 9, since negative 9 times negative 1. Redistributing then, I'll have x cubed plus 9x minus x squared minus 9. And finally, putting our function in descending order, we have x cubed minus x squared plus 9x minus 9. We found a polynomial of degree 3, which contains the zeros we're looking for. Let's find a polynomial again with a degree 3. This time we know our x values are negative 5, the square root of 3, and negative square root 3. Our factors then are x plus 5 when we add 5 to both sides, x minus square root 3, and x plus square root 3. This will be our function, and we'll go ahead and distribute. The first two sets here, or excuse me, the last two sets with the square roots of 3, I see that they're conjugates. And by using conjugates first, we're able to simplify our polynomial a little bit easier. When I distribute, we'll have x squared plus x square root 3 minus x square root 3 minus 3. Keeping in mind that the square root of 3 times the square root of 3 gives us the square root of 9, and the square root of 9 is 3 itself. we now will have x plus 5 times x squared. Our positive and negative x square root 3's disappear, minus 3. Distributing one more time, I have x cubed minus 3x plus 5x squared minus 15. Writing our polynomial out in descending order, we have x cubed plus 5x squared minus 3x minus 15. We found a polynomial of degree 3, which will have the zeros listed. Let's find a polynomial. This time we have degree 5. We have -1 with a 0 of multiplicity 3, 4 as a 0 with multiplicity 1, and 0 as a 0 of multiplicity 1. So our x values then we know are going to be -1, 4, and 0. When I add 1 to both sides, I'll have x plus 1, but this has a multiplicity of 3. So we have a multiplicity of 3. X minus 4 has a multiplicity of 1, and x is already by itself, and it has a multiplicity of 1 as well. I know that x plus 1 cubed is the same as x plus 1 times x plus 1 times x plus 1 times x minus 4 times x. I'm going to first start and just work left to right. I don't have any conjugates, so I'm just going to start and work left to right. I'm going to first start by working on these two values here. Those two values, when we multiply, we'll have x squared plus x plus x plus 1. So combining like terms, I have x squared plus 2x plus 1 times x plus 1 times x minus 4 times x. The next two I'm going to do is the trinomial times the binomial here. This will give us, when we distribute, x cubed plus x squared plus 2x squared plus 2x plus x plus 1. Combining like terms, we have x cubed plus 3x squared plus 3x plus 1, all times x minus 4 times x. So continuing on, take the polynomial of our degree 3 times our binomial. This will provide us then with x to the 4th minus 4x cubed plus 3x cubed minus 12x squared plus 3x squared minus 12x plus x minus 4. Combining like terms, we'll have x to the 4th minus x cubed minus 9x squared minus 11x minus 4 all times x. So our function value will be, once we distribute the x through, x to the 5th minus x to the 4th minus 9x cubed minus 11x squared minus 4x. So we found a function that has a degree of 5 with the zeros of -1 multiplicity 3, 4 multiplicity 1, and 0 with a multiplicity of 1. Example 4. Find a polynomial function. This time we also have degree 5 with -½ as a 0 with multiplicity of 2, 0 as a 0 of multiplicity 1, and 1 as a 0 of multiplicity 2. So I know that x needs to equal -1/2. x has to equal 0 and x is equal to 1. When I start solving for x is equal to negative half, yes, I could say, well, x plus half is 0, but then we know we're going to end up multiplying by fractions, and sometimes we don't like fractions, so let's try to keep it a whole number. I also can say, well, to get rid of this fraction is to multiply both sides by 2 and then add 1. So 2x plus 1 is the same as x is equal to negative half. This has a multiplicity of 2. X by itself has a multiplicity of 1. And x minus 1 also has a multiplicity of 2. And this will be our function. To expand this a little bit more, I know this is going to be 2x plus 1 times 2x plus 1 times x minus 1 times x minus 1. None of these are conjugates of each other, so I'm just going to work myself left to right. I'm going to start by taking 2x plus 1 times 2x plus 1. This gives us 4x squared plus 2x plus 2x plus 1. Simplified then, we have 4x squared plus 4x plus 1 times x minus 1 times x minus 1. Just going to do the next one here. This will give us 4x cubed plus 4x squared plus x times x minus 1 times x minus 1. Let's work on the trinomial times the binomial. We now have 4x to the 4th minus 4x cubed plus 4x cubed minus 4x squared plus x squared minus x. I do see that I have two terms that are able to cancel or make a zero pair. 4x to the 4th minus 4x squared. Oops, excuse me. We can combine like terms with our x squareds. So negative 3x squared minus x. And finally, we need to multiply that by the binomial x minus 1. 4x to the 5th minus 4x to the 4th minus 3x cubed plus 3x squared minus x squared plus x. For a final function in the 5th power of 4x to the 5th minus 4x to the 4th minus 3x cubed, combine like terms here, plus 2x squared plus x. So we found a polynomial of degree 5 that has the zeros that were listed. You've probably noticed in the first couple of examples that imaginary numbers always come in pairs. They always come in pairs, and that's always going to happen. And they're always going to be conjugates of one another. So if we have a plus bi, we will also have a minus bi. If we have 2 plus 7i, we also know that we have 2 minus 7i. They always come in pairs, and they always come in conjugates. The same is true with irrationals, also from the first page, that if we have a radical, they always come in pairs as well. So if we have negative 3 plus 5 square root 2, we will also have negative 3 minus 5 square root 2. So they always come in pairs. It's telling us that suppose a polynomial function of degree 4 with rational coefficients, we have 6 minus 5i and negative 1 plus square root 7. is 2 of its zeros, what would the other zeros be? Well, if I look at 6 minus 5i, I also know that I'm also going to have 6 plus 5i. If we have negative 1 plus the square root of 7, I know I'm also going to have negative 1 minus the square root of 7. So we have found 1, 2, 3, 4. It's asking us to find the other zeros. With degree 4 means that we're going to have 4 zeros. They could be imaginary or complex, and they could be real number zeros. Suppose that a polynomial function, we have degree 6, so we know we need to find 6 of them. What are the other zeros if we are given negative 2 plus 5i, negative 2i, and 1 minus the square root of 3? I also know I'm going to have negative 2 minus 5i, positive 2i, and 1 plus the square root of 3. So I have found the 6 zeros that match. Taking that a step further then, it's asking us to find a polynomial function of lowest degree with rational coefficients that we have negative square root 3 as well as 1 plus I. I know that x is going to equal negative square root 3. So then I also know that x is going to equal positive square root 3. We know x equals 1 plus I, so we also know that x equals 1 minus I. When I get it set equal to 0, I'll add square root 3, so I'll have x plus the square root of 3. On the next one, I'll have to subtract square root 3. Here I need to subtract 1 and subtract I. So I'm going to have x minus 1 plus I. And I'm also going to have x minus 1 minus I when I'm combining, or I should say when I'm factoring out that negative, kind of keeping those I values together, and I'll show you how that will work. I'm going to multiply these in two separate pieces here. I'm going to do the radicals and then the imaginaries separate from one another because they'll simplify really well because they are conjugates. We'll start with the radicals. I have x squared minus x square root 3 plus x square root 3 minus the square root of 9. I see that our middle two terms cancel, so I'm left with x squared minus 3, which is super helpful. All right, I'm going to rearrange my terms a little bit here. I'm going to rearrange them such that I'm going to have the x minus 1's parentheses together minus I and x minus 1 plus I here. So I know that when I distribute here and here, I'll have the subtract 1, and I'm just going to rearrange my parentheses, and negative times a positive gives me the negative here. Similarly, when I distribute the negative here, I'm going to have x minus 1 as well, and negative times a negative becomes that positive I. Now when I distribute, I'll have x minus 1 times x minus 1. Well, I know that x minus 1 times x minus 1 will actually have to redistribute. Then I'll have x minus 1 times I, so I'll have positive I times x minus 1 minus I times x minus 1, and negative I times I is negative I squared. Notice then, by doing this, I'm able to cancel these middle terms here, and this we replace with negative 1, which ultimately turns into a positive 1. Then I'm going to go ahead and distribute our x squared minus 1, providing us with x squared minus x plus 1, and then plus our 1 from over here, providing us with x squared minus 2x plus 2. So
So x squared minus 2x plus 2. We now have to distribute our binomial times our trinomial. Going to erase all of this stuff over here so we have some more room. And then we'll go ahead and distribute. We now have x to the fourth minus 2x cubed plus 2x squared minus 3x squared plus 6x minus 6. Combining like terms, then our function will provide us with x to the fourth minus 2x cubed minus x squared plus 6x and minus 6. Find a polynomial function of lowest degree with rational coefficients that has negative 5i as one of its zeros. So if I know that x is equal to negative 5i, I also know that x has to equal positive 5i. My function values will now be x plus 5i and x minus 5i. And we can go ahead and distribute. We now have x squared minus x5i plus x5i minus 25i squared. In the middle, our terms create a zero pair. I also know that I'm going to replace I squared with negative 1 for a final function of x squared plus 25, since negative 25 times negative 1 is a positive 25. Okay. It says, given that the polynomial function has a given zero of 4, what are the other zeros of the polynomial? I know that a 0 is 4, so I'm going to find a reduced polynomial. Again, we're going to use synthetic division. I see it's written in descending order and there are no missing pieces. So I'll bring my coefficients 1, negative 6, 13, and negative 20. I'll bring down 1. 4 times 1 is 4, which provides us with negative 2. 4 times negative 2 is negative 8, which is 5. 4 times 5 is 20, and we get a 0. It should not surprise us that we have a 0 as a remainder, because it does tell us that 4 is a 0. But now we have a reduced polynomial here, 0x, x squared. Our reduced polynomial is x squared minus 2x plus 5. I don't think I can factor this because there's nothing which multiplies to 5, but yet adds to negative 2. So we will have to use the quadratic formula to help find the other two zeros. I know that I need to find 3 of them. I already have 1. So our A is 1, our B is negative 2, and our C is 5. X equals the opposite of B. Opposite of B is negative 2, so positive 2. Plus or minus the square root of B squared minus 4 times A times our C value all over 2 times A. 2 plus or minus the square root of 4 minus 20 divided by 2 using the order of operations. This gives us 2 plus or minus the square root of negative 16 over 2, which gives us 2 plus or minus the square root, of 4i, since the square root of negative 16 is 4, and we get rid of that negative by the I value, all divided by 2. All these pieces here, all these coefficients are divisible by 2, so that simplifies to 1 plus or minus 2i. Our x values then, we already found one over here. So our x values are 4, 1 plus 2i, and 1 minus 2i. We found the 3 zeros that we are needed for this function, or this polynomial, excuse me. Given that the polynomial has a function or a 0 of 2, find the others of x cubed minus 8. We are missing the x squared and the x value. I know that 2 is a 0, so let's find the reduced polynomial. I'll have 1. We have 0x squareds, 0 x's, and then negative 8. Bringing down the 1, 2 times 1 is 2. When I add, we have 2. 2 times 2 is 4, so I have 4. 2 times 4 is 8. Should not be a surprise that we get a 0 here. 0x, x squared, so I have my reduced polynomial of x squared plus 2x plus 4. There's nothing again that would multiply to 4 but yet add to 2. So we're going to need to use the quadratic function or the quadratic formula. A is 1, B is 2, C is 4. So x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Negative 2 plus or minus the square root of 4 minus 16 over 2. Negative 2 plus or minus the square root of negative 12 over 2. 12 we can simplify to 4 times 3. So since I can take the square root of 4 and I'm going to take that negative out, we now will have negative 2 plus or minus 2i square root 3 over 2. Notice that our coefficients are all divisible by 2. Negative 1 plus or minus I square root 3. So our x values are 2, which they had already provided us, as well as negative 1 plus I square root 3 and negative 1 minus I square root 3. The largest exponent we had was 3, so we had found all 3 of our zeros. And this concludes our first day on finding zeros using theorems of zeros, and then next time we'll talk a little bit more about what happens if the request doesn't give us a 0. How can we identify what all of those zeros are if we're not given one to start with?